Okay, next thing to talk about. And tonight's just scattered odds and ends. So we looked at a few things before the break for the sake of the video. They're not watched consecutively like it's happening here in the classroom. Scattered topics tonight. So we looked at ChatGPT and generators, and what we did before the break doesn't really relate to what we're getting ready to start into now. Big thing for the 200 level class, programming class, is usually diving into object-oriented programming with a little more depth. We're going to start on that tonight. And I always like to start with a picture here. Has everybody had some biology anyway through education? Like not even a college level biology. You have like a 7th grade science class that had a biology chapter and see what we call the tree of life.
Sure.
Everybody seen that? We categorize things up at the top. There's just that general catch-all that we call life form. And there's certain characteristics that it means to be a life form. It's a story I really like from the early days of SDEV, Search for Extraterrestrial Intelligence. One of the early scientists working there, his grandma came to see what he was doing. He's graduated from college. She wanted to see it and was looking at their labs, and they were talking to her. All the scientists there were gathered around talking to her and talking about how they were worried about figuring out how to define life when they found it. They weren't sure what to do. This old lady just looked at him and said, well, it's easy. Life is squishy. So that's all you need to know. And that's what she meant by that. And said that means you'll know it when you see it. So I thought that was like the best description ever on how to define life. If it's alive, you'll know it when you see it.
You say life is squishy?
Squishy. That was the term this old one of the first scientists said his grandmother used that term. It's squishy. That means you'll know it when you see it. You'll see it. You're like, that's alive, and that's not alive. That's our basic characteristic, right? So life form, that all-encompassing thing, that's the squishy stuff. But then we break it down into categorize, because humans like patterns. We like to categorize things and develop patterns with those categories. In particular with life form, there's 3 categories that it goes to. And this is a tree, but I'm going to draw it with the root at the top and the tree going down. You probably used to see in the picture with the root at the bottom and the tree going up, but this is a computer class, and in computers, we almost exclusively draw the roots at the top when we draw trees. So life form, there's 3 different types, right? There's archaea, bacteria, and eukarya. I think I spelled that wrong, but whatever eukarya is, I think there's another U in there somewhere. Complicated word to spell. But 3 categories, and there's different properties about those. We can keep adding details. So we take all the things that it means to be a bacteria and split up into a couple different versions that I'm not even going to try to spell. I'll put E. coli and Staphylococcus. I'm just going to abbreviate that. I'm not even going to try to spell that word. But those are the 2 big ones. Anybody's had a biology class, you remember the pink and purple dyes? Okay. They're 2 distinct types of bacteria, and we can immediately tell it based on whether a certain type of dye turns pink or purple. A very, very common test to run. Which is the shape? Are they circular or are they cone shaped, rod shaped? But more details than just bacteria alone has. Same thing for eukarya. There's a branch that might have plants, and another one that has fish, and another one that has mammals.
Taking me back, Chris. Reminds me of kingdom, phylum, class, order, family, genus, species.
Yes. Kingdom, the phylum, that is what that is. Exactly. But we add details at every level, right? Take all the stuff that means to be a eukarya. I guess there's some single cell eukarya as well, but somewhere down that chain is multicellular, and then we get into scale, more details. Everything that it basically means that centralized nucleus in all the cells, the way the chromosomes are structured, the mitochondrial DNA, all of that basic properties, and we add things like scales and gills, or hair and memory glands, and it keeps getting more and more detailed, right? Because we can take everything it means to be a mammal and be an elephant or a dog or hominid. More and more details. I'll just write human. There's only one type of hominid. There's multiple hominins, but there's only one hominid, so we don't need multiple versions of that. And we can keep going adding details, right? So everything that needs to be a mammal, and we add some details for the next level. And it just keeps going and going and going. So like maybe a black lab or a Chihuahua or beagle. Chihuahua wasn't going to fit in the circle after a lot of letters in that word. Everybody's seen the tree of life before, right? And the reason we start learning this young and remember it, like Tim just rattled off those words, rattled off the main levels. Some levels are more important than others. The reason we see that and can remember that is this is how humans naturally categorize things. We start with the most general thing, then we add some details. We take everything that it means to be that and then add more details to it. So we start generalized and get finer and finer grain detail as we go down the tree. And then different ways we can approach stuff. If we need any random life form, any one of these bubbles will work, right? But if we need to say an elephant, there's only one bubble we can use. If we needed a dog, we have two options. So everything below it generalizes to that bubble. So that's the way humans naturally categorize things. And the reason I started with that diagram is if we started making a computer program and needed virtual representations of something, animals are a common example, so let me do that up here. We could start at the top with a generalization of everything it means to be an animal object in our program. So maybe it's a software for a vet's office. So vet's office is going to need an animal type of data, which is a big thing. A lot of people aren't sure how to take objects at first because it looks like a big program, right? But an object is not comparable to a program, nor is an object comparable to functions. Objects contain functions. An object is a data type. So an object goes with like integers and floats and booleans. It's a type of data, but it's more complex than those simple ones I just listed. It's built up of a lot of those simple ones and maybe even some other complex ones. But it's built up of other data, a complex data type that fits our particular needs. So a new type of data. So for a vet's office, we need some animal data. And there's going to be certain traits about that. We might do that example. The big example is going to be next week when we get into abstraction. But there's different things that can happen. We can break that down. Certain animals are going to be more likely to come to the vet's office than others, right? We're going to see mostly felines and canines. If we're out in a farming community, the vet's probably going to see a lot of bovines. Right, the different types of animals that it's going to see. And well, I guess from canine, could be one of the wild ones, wolf or fox. Those get brought to the vet's office usually when they're injured, not regular clients, but dogs would come in a lot. And then once again, we have different types of dogs and we're adding details as we go down. I'll put Chihuahua here. And write the word before I draw the bubble. Or Black Lab. Different types of dogs. They both take everything it means to be a dog and add in different sets of details. And when we make objects and draw a diagram to keep them organized, because again, everything that fits in the classroom is going to be small, nice and compressed, but the world at large has moved to much bigger software development problems than we could possibly even really talk about in a classroom. So there's that big jump at graduation, just to remind you all that that's in your future ahead. To jump from the classroom to modern software development it's not just a little step up. It's a big difference. Because there you'll have years to work on programs, years to work on very complicated programs. But when we diagram it out to organize it and make sense of it and try to think about stuff, because in the modern world, we're going to be working with big, difficult problems, right? Like ChatGPT. How do we make it so that, how do we make it so that this machine feels like interacting with another human instead of like Alexa, where we just bark orders at it? Might understand our language, but most of the assistant stuff, we just bark orders at it. And that's not the best way to interact with the machine. For one, has anybody seen like 3-year-olds that get used to Alexa? And then maybe get a couple years further on, 7 or 8, and all they've learned how to do is bark orders and stuff. So that's how they interact with each other. Some of y'all might have some younger siblings in that range. They learned to bark orders at Alexa when they were 2 and 3 and first learning to speak. And that's how they know how to communicate. So that's how they communicate to other people as well. Not a good way for humans to communicate. We want it to be more natural communication. So there's a lot of thinking involved in that. And notice the pictures are the same. That's why I started with this. This is how humans naturally categorize things. This is how we categorize things in object-oriented programming, and that's the advantage of it. We get to think like a human again. Obviously, we still have to do the algorithmic coding orders. Yep. Little things like that happen. It's impressive what kids can do with technology. Responding to the chat room there. So we still have to do the algorithm and coding things, but when we put them together, put the pieces together, we get to think like a human. We categorize them like a human again. And it's good for a human, bad for the machine. I'm just going to make up a number here because obviously this would be different for every situation. But an example of how good this is for the human, right? If the programmer can do 1,000 times more, I'm not a chalkboard out. Give me in the middle of writing a word and it's just going to stop on you. So if the programmer can do 1,000 times more, right, plus 1,000, and we do that at have a 10% loss in efficiency because we passed a whole bunch of extra work onto the machine, minus 0.1, we're still at plus 999.9. It's still well worth it. I just made up those numbers, but that's the sort of trade-off we get from object-oriented programming. The programmer can do 1,000 times more, and the machine does a little bit of work by giving the machine extra work. It's going to be nice when we can to buy back that efficiency we lost. There's ways to do that. We worry about that a lot more in C family of languages. With Python, we're not very efficient anyway. So when we do something that loses efficiency, it escalates quickly, but it is definitely to the programmer's benefit. So it was invented, object-oriented programming was invented in early 60s. I think 1962 is the date that's actually given on it, but the guy thought of the idea a couple years ago before that and debugged it for a couple years after that. But there in 1962, the date that's marked on it, right? It's this guy spent years on that before and after 1962 on this idea. And in 1962, it worked fine on the biggest computer in Norway, which is an incredibly rich country. Right? Y'all have heard of Norway, right? One of the richest countries in the world. So and a high member of NATO. So in 1962, the nicest computer in Norway was one of the nicest computers in the world. America or Russia might have had a nicer computer, but probably not. And if they did, it was a top secret thing that very, very few people knew about. So it worked great on the nicest computer in the world, 1962. Wouldn't run on the typical computer. But as years passed, machines improved, and by about mid-1980s, what we would call the average machine could handle that extra overhead that comes with object-oriented programming. And around that point, we pretty much switched to object-oriented programming and never looked back. It is rare that you will see a program in language that is not object-oriented these days. You all saw that in your previous class, right? Python is only an object-oriented language. There's some shortcuts built into the background. They're actually big, complicated things when we look at disassembler and see the assembly language that actually runs for those shortcuts. We can make it look like a procedural language for introducing people, where we just put variables and stuff, and we don't have to define classes and put every single thing into functions. But there's a big, complicated workaround for that. When we get around to looking at disassembler, we'll see how much actually happened, what it takes to do that. So it looks like a procedural language, but it's not. It's still object-oriented. And pretty much every language that we would use in the modern world is an object-oriented programming language. Even Lisp, which was created in 1959 and is still used for certain things. It's probably Scheme these days, which is object-oriented Lisp, created modifications made long after 1959. But we pretty much, once computers could handle it, we haven't looked back because it's so much better for the human. We're the ones that make the decision. So we decided to do the one that's better for us. I've made the joke a few times that in Hollywood or in movies, they always have that big plot point of machines are mistreated and rebel against humanity. And in reality, people put googly eyes on their refrigerator and give it a name, right? If machines are mistreated, it's all the Python code we make them run. When you look at the background stuff, that's a mean thing to do to a machine. There's a lot of work there, but luckily they don't complain about it. So, in object-oriented programming, the idea, 3 concepts that include all this. 3 concepts. The first one is encapsulation. That's what you looked at in the previous class when it was introduced in the 140 class. I like to know how the word capsule is right in the middle there. So like a time capsule, right? Time capsule, you'd take a bunch of artifacts that are reminiscent of what it means to live in 2023, which would be a computer. So maybe go back to the time, like the 1960s. Time capsule from the 1960s, you grab probably a newspaper about what NASA was doing on the space race, and some vinyl records of the great music that came out in the 1960s, a pair of Chucks that were more comfortable, Converse Chucks that are still on sale and have never stopped selling since they were invented in the mid-60s. So much more comfortable than pretty much every shoe that had ever come before. Almost the model of all the shoes we wear in the modern world. Even when unless we're wearing dress shoes, the old uncomfortable style, we can kind of tell that our shoes are a descendant of Chucks. The super comfortable shoes and everything that it meant to be a lot to represent the 1960s. We put that in a box and bury it, and somebody would dig it up later and can see it. But everything would be included. So everything the object needs is included inside of it. I drew an animal object up there. If the animal You're gonna need a name, a weight, an age, previous visits, allergies, all that stuff that an animal piece of data would need for a vet's office needs to be included in that, in the data type we're creating. And sealed up. Do I have open close principle? I'll put open close principle on here in a moment. That's something. So you would have seen some of that in the first class. Everything it needs is included. Everything object needs is included. The second option, which I probably should have left one of those pictures up there to point at, is inheritance. Which we can think of how we use that word in English. People spend their lifetime working and building up some sort of savings. Hopefully, that's not always the case in America, but hopefully that's what happens, right? You spend your lifetime working, buy a house, and build up, say, accumulated a lifetime's worth of stuff. And eventually your kids are going to inherit that stuff, right? And then they'll add to it what they can build up in a lifetime. And then their kids will inherit that stuff. So things get passed down through generations. So the same thing, everything this object needs is included. But like that picture that I already erased, you probably should have left up here. We have that very generalized one, and then we have more specific ones down below. Animal, we have dog and cat, and then types of dogs. Beagle or pit bull. All the little, we add details as we go down. It inherits everything it means to be a dog, which already inherited everything it means to be an animal of that vet clinic, and adds a few more details to it. Oh, that's why I wrote the open close principle. It's in my notes here. So an important one that involves those two is what's called the open close principle. And this is something you will have to answer a lot of questions about. We don't have any quizzes in this class, but when you go to get certified as a Python programmer, you don't get certified as a Python programmer by writing Python code. You get certified as a Python programmer by answering multiple choice questions about Python. So everybody seen that? Like when the new statewide shell was made, I wasn't very happy about the absence of quizzes. I'm probably going to put that back in before the next time I teach the class, because we need to get practice answering those multiple choice quizzes. And a lot of the quizzes, the Java class especially, the course shell for the Java class, it looks very, very similar to the certification exam for Java. Almost like somebody took an old version of the Java certification exam and copied and pasted those to make the quizzes for that class. Surely have that, something like that for the Python quizzes, right? Because that's what we have to do to get the certifications. We need to practice those. And this is one you'll see there, open close principle. If you're heading under a 4-year degree, you'll get asked lots of questions at it at every level along the way. And get to know it very thoroughly. But what it is open, objects are open for extension, closed for modification. So once we encapsulate that top level, the capsule is sealed. We can't put anything else in there. If we need to put anything else in there, what we have to do is make a child of it, make a child of that parent, which is one of our terminologies, parent class, child class. You'll hear different terminology. We also have base class and derived class, as well as super class and subclass. You will hear all three. They're interchangeable, but as pairs. We would never say super class and derived class. Super class always goes with subclass. Parent class always goes with child class. So if, once we've created it, it's closed for modification. That's what we get from the libraries. Right? All those libraries that are already built in Python that we import and then use that to build other things. We don't change the original library, the original module. We extend it with new functionality. So that's the open close principle. You will definitely see questions about that somewhere in your future. Unless you just jump in a job and you don't ever take any certifications or anything. You will most likely see I guess I shouldn't say definite, nothing's definite in this universe, right? Our third concept is a really big word for a really simple concept. Polymorphism. Big fancy sounding word. I like to use this analogy for polymorphism. Let me draw a picture of a hammer here. Everybody know what a hammer is? I assume so, right? There's this thing that's weighted. It's a combination of levers. So multiple levers combined. This simplest physics explanation on a hammer. And typically we use it to pull with this side and, push with this side and pull with this side. Normally fast enough that we would say hit and fry, but we can push and pull things slowly with a hammer, right? There's nothing that stops us from doing that, from moving slowly. But that's two uses, right? That's multiple uses for the same tool. That's what polymorphism is. A hammer is a nice heavy object. What I really like about this analogy is we don't know what to do with that, right? We're going to use it to hammer in nails, maybe pry some boards apart if we're doing demolition, knock things down. General uses of a hammer. But if we're out there on a construction site, a hammer is a nice heavy object everybody's going to have on them around that construction site is going to have one, right? Which means on a windy day, it's perfect for holding down a set of blueprints. But would we ever say that's what a hammer is for? That's what polymorphism is. Different uses for the same tool. We develop a tool and we can use it for different things. Example for coding, if we made an object that was designed to deal with averages, had a bunch of math stuff or statistics, somewhere in there is going to be stuff to do an average. And to do an average, just a regular average, we add up a bunch of numbers and then divide by how many we have. Which means there's a function or a method in there. We use those words interchangeably, the technical version, the one that would be the right answer on a multiple choice quiz, like a certification exam. Methods go with object-oriented programming and functions go with procedural programming. But we don't really do much coding in Fortran anymore. Everything we do is object-oriented, so it's really all methods. But the correct answer on a quiz is the methods go with object-oriented programming. But in that object I just described, there's going to be a method to add a bunch of numbers together. So we could use to that anytime we needed to add numbers together, not just when we take an average. Add numbers together and then divide by 1 so that it doesn't change it. We just get a sum. But that's not the purpose of it. It's just another way we can use that same tool. That's what polymorphism is, different shapes. And this thing confused me for the longest time with these diagrams, because we always think about inheritance. And when we're designing stuff and designing our objects, classes, and then objects, and designing classes, instantiating objects, putting all this together, we think about inheritance, adding those details to that generalized version. So I just felt like those arrows were going the wrong way. Arrows are polymorphism. I guess I always thought it went with inheritance, but the arrow shows polymorphism. If we need any random animal, every arrow here points at it, right? So every one of these objects could be used as an animal. If we needed a dog, we have two options here. A cat's not going to work where we need a dog. We don't have a strictly typed language. That shows up a lot more in strictly typed languages. where we have to worry about those data types. Python, one of the reasons it's slow is that it will take time to figure out what our data type is in the background. But then we still have that polymorphism and stability of one tool to be used as another. Many shapes. So hammer. It's a nice heavy object. It also makes a great doorstop. If you're on a construction site or remodeling your kitchen, carrying a bunch of stuff in, you got to carry a bunch of stuff in. A hammer is going to work great to prop open your door. But if somebody asks us what's a hammer used for, would we ever say it's a doorstop? It's used to hold open the door when we carry things inside. It just also works for that. And that's the third concept, is multiple uses for our tools along with the original design, so that we don't have to make a new tool for every single task that needs done. We can use the existing one with the open close principle and grab one that has a bunch of the generalizations we need, and then add the finer details we need for our particular use. That is how we extend it. Ability of one object to act as another. I'll phrase it that way. Ability of one object to act as another. I just wrote that sentence with a pen, but maybe it's the side of my head. It's just, I can put the cat back on the pen and scratch that. But does that make the marker a scratching something? Scratching, what's the back scratcher? Yeah. If I do this, does that turn that marker into a back scratcher? It's still a marker. It just works for a back scratcher. That's polymorphism. So a big word for a simple concept. It's okay if I erase this stuff over here. I'm gonna leave those key principles up there. So I'll erase these pictures. So a couple important terms. Terminology. When we talk about parent, child, superclass, subclass, base class, derived class, but class shows up everywhere. That is the design, or we can think of it as the blueprint for our object. It's a great example of this in modern America. Everybody's familiar with subdivision, right? The classic American subdivision. There's lots of them all over the place. Just any random subdivision, you've seen them before, right? One thing about subdivisions is they usually build similar houses in them. Right? So a subdivision full of 2-bedroom ranch homes. Used to be a farm or something. They took 10 acres and stuck in 20 2-bedroom ranch homes. They're all 2-bedroom ranch homes. They're built from the same blueprint. That's the class. So object or instance is the thing we make from that design. Made from design. So in the subdivision, the blueprint is for a 2-bedroom house. And we're going to make them all the same. And then when we create those objects, the actual house that people are going to live in, they're not all exactly the same. They follow the same blueprint. They're all 2-bedroom ranch homes with a garage and a basement. But maybe some of them have the garage on the left and some of them have the garage on the right. Some of them have square windows in the door and some of them have round windows in the door, or triangle windows in the door, or a half moon window above the door, and others have windows down the side. Some of them have a half basement, some of them have a full basement. Different types of shutters on each one, different doors, little differences that are particular to the real version of it that didn't need included in the blueprint. But they're all based off the same one. Whittier is probably the best example of that. Anybody familiar with city of Whittier in LA? It's where the original Wonder Years series was filmed. 120 square miles of 2-bedroom ranch homes built early 50s when LA first started expanding. So basically it's 120 square subdivisions grew and they grew into each other and became one city. And it's 120 square miles of 2-bedroom ranch homes. But they're all slightly different and unique, especially the actual object or the instance of them, not the design. The design was all the same. But the things built off that, especially now that it's 70 years later, a couple generations of families have lived there. They've all been remodeled, and they all have their own little custom touches, unique things, changes that have been made, and slight differences between them. That's the analogy how that fit in. That's what when we create it, we make the design for it, and then over in our code, I don't know. We'll have that class, my object, is a class, and we create it, and then over our code, we'll say X equals my object. And that gives us a new instance called X that we can refer to any of those data fields and methods in my object with. Put it into the code because I'm behind where I planned on being here. So I don't know how far we'll get in the code example this evening. I want to make sure there was lots of time to do stuff, because we talked about generation, right, which is something that you're going to want to get some practice with. And we also talked about ChatGPT, that's something else you're also going to want to get some practice with. So I'll make sure there's plenty of time to do stuff. 2 more words here. It's okay if everybody sees 2. Everybody should have heard those terms in the previous class. So review. This next one you might not have heard in the previous class, but it's an important one. Composition and aggregation. I heard come across those words before. So let me put some normal English words to help keep them straight. Composition is a relationship. Aggregation has a relationship. I've been using a lot of analogies tonight. So with an analogy, think about materials. You may have heard the word aggregation used with concrete. The aggregate concrete is when we lay concrete and then strip off the top layer. Usually there's fancy chemicals you can put on it, but dish soap and cooking oil work even better than the really expensive stuff. So most contractors do that. But we take off that top layer so we can see all the gravel inside of it. That's an aggregate. A composition, if we just went out and took a shovel full of dirt somewhere in southern Indiana, we're going to see dirt and rocks and in modern world probably some trash and a whole bunch of different things. But they're separate pieces, right? We could run them through different sieves and separate them. But those rocks that are in that concrete, they're permanently there now. So an aggregation is a permanent, is more in how the connection goes. It's similar to that.
Chris, I'm sorry. You said so aggregations kind of like the concrete and the compositions like the shovel of a whole bunch of different minerals.
A whole bunch of loose things, a pile of sand.
Okay.
We call it sand, but it's actually a composition of a lot of different things. Any beach in the world is crushed up shells, flakes of granite, flakes of limestone, all sorts of different things, but we would call it all sand. It's composition. aggregation is more connected, but still separated. Like in concrete, when we do aggregate concrete, we take off that top layer so we can see all the rocks in there. So, well, not just seeing it, that looks, a lot of people like to look at that, but that also gives us better traction when it's icy, right? It's not a perfectly, the ice becomes bumpy, so we get, it's not as slippery as if we had a perfectly smooth level of concrete with ice on it. That makes it even smoother. But they're still separate things, but they're connected. That's how the connection goes. That might not be the best analogy. I have a long list of analogies, but to use these, what I put here, I have put name and address here. So a person has a name, or a name is a person. Which one of those would make more sense?
Person has a name.
Because the alternative, the other thing I was going to use is an address. Is goes with the name, right? That is the person's name. So if the person has their current address, the address is a lot more likely to change than the name, right? That's the composition and aggregation. That's why I highlighted these words. A composition is a relationship. It's somewhat permanent. An aggregation is more separated, because would that name still exist without the person? Somebody else might have the same name, but without that person, that name doesn't really mean anything. But what about their address? Without the person, somebody else could live in that address. So the address is an aggregation. It has a relationship, but it's not as permanently locked together. Not that it is a relationship. We'll see those. I'll try to bring in more examples. But think about name and address. So like in student records, a student ID, that's all unique for all of us, right? We have that C number, or you're here at Ivy Tech. But when you graduate, nobody else is ever going to have that C number. It only exists with you. But also in those records is your address. And well, you can move and still be a student, and that wouldn't make any difference whatsoever. There are students at Ivy Tech without an address. The ones that always spring to my mind was a couple people that I was always super impressed with. Their they both grew up in an orphanage and had a baby. So when they hit 18, actually they weren't 18 yet, but they had a baby, so they were out of the orphanage. They lived in the car and raised the baby while they got their degrees. I was always super impressed with it. It's like that's some hard work, because they had nothing. They had they had the address of the orphanage where they grew up in. It was a while before they even had a car to live in. So to be a student, you have to have you have to have that student ID number, but you don't have to have an address. The way they're connected is different. And we'll often hear it used as is and has. And as you see it in more situations, remember those. A composition is a relationship, and an aggregation has a relationship. You are your name, but you have an address. Kind of the way to remember those. It's already past 8. This is taking longer than I thought. So now to the Python stuff. This is something that, again, you're quite likely to see questions on. For certification exams, you will definitely see questions on that. So I'll work those in examples, but at first it seems confusing, but after you see it a few times, most people do fall back on that is and has seems the best way to remember it. So now some Python stuff. Everything in Python automatically inherits from a class called object. So up at the top, we have this class object with a lowercase o. I should try to make that clear. Because we might need to refer to it in our code at some point. There's this object, and there are a few things that we have to work with already. And we can identify them because they have double underscores before and after a word. The two underscores before the word have meaning. The two underscores after the words are because the person that invented Python likes symmetry. They kind of have some meaning. Sometimes we'll parse through them. There are functions that manually look for those two underscores afterwards. So they do stuff. I shouldn't say they don't have meaning, but the two before definitely mean something very important to the machine. One of the most common ones is underscore underscore str underscore underscore. And I'll put self there. That's the toString method. So we saw this earlier tonight. It had math.py, and then before it I wrote string. So I'm on the board, I'm going to leave off the math dot and turn that into a string. This method that y'all have seen before, what this does is calls this method. So that's something we do a lot. Humans communicate through text and pictures. So whatever type of data we have, we need a way to turn it into a string. And the default is to tell us where that's located on the RAM chip, which is, I guess, useful for the Python interpreter, not very useful for a human. So we almost always want to do something with that. We want to go in and override that method. The most misused word in Hollywood. Override means change the default value. Next time you see him say that in a movie, picture that same character saying, I'm going to try changing the default value. And it really makes the end of the solution at the end of a lot of movies quite ridiculous. Like, oh, should change the default value a little bit sooner. We saved a whole lot of trouble in the movie. Another one we have is equals. We almost always want to do something with this.
You said override is change the default value.
Yes.
Okay.
Override just means change the default value. Contrary to what it seems like from Hollywood. I guess it sounds fancy. That's why they use it. Equal. We also have LT, GT, LE, GE. Y'all can figure that out. All of the comparisons. Underscore, underscore, two-letter version of the comparison. The obvious two-letter version, then underscore, underscore. There's better ways to do greater or less than this. So a lot of people like to manually write something together for that. But equality, we need a way to what makes two objects equal. On the example I started with earlier, the veterinary clinic. What does it take to make two animals to be equal? We look at reason they're at the vet. Would a scheduled checkup and an emergency call be equal? Probably not. A scheduled checkup can be delayed. It's like there's an emergency that needs addressed first. So that wouldn't be a good equality. Age. If we're talking about like the age of two chihuahuas, that might make sense. What about the age of a chihuahua versus the age of a turtle, one of the giant tortoises? The oldest dog on earth is currently a chihuahua. So I threw that example out there. And it's in its 20s. But turtles regularly live well past 100 years. So a 20-year-old turtle is still like a baby turtle. So age wouldn't necessarily be a good one. Weight. There's not a good answer. The answer is, what do we need it for? What's our situation? So if that is a very situational question, Python has really good memory management. Mentioned that before. It has great memory management, terrible memory usage. Luckily, we'll eat up the whole RAM chip, but it'll be nice and organized on that RAM chip when we burn through the whole thing at once. So the default is it will only work if it's the exact same object. So if we already have a 3 stored somewhere, back to the stack heap diagram. So one place in our code, we store a 3 to this variable X. And then at some point later in our code, we have a Y that also needs to store a 3. It's not going to make another 3. It's like, oh, I'm already storing 3, so you can just refer to that as well. The really good memory management. It doesn't need to store it twice. So those two would be equal by the default version. That's why we can say 3 equals, right? If X is equal to Y, well, they're both pointing at the same spot in RAM. So they are equal by the default version, but not always. And when we type equal, that is a call to this method. So you want to override that so you can use this symbol in your if else structures or your while loops. Because we're used to the other types of function calls, but remember a human put this together, and this is a much older one, but that is a function call. And that is a function call to this function. There's lots of them. A few others, again, with the stack heap diagrams. Before we get to the data structure thing, where I'm going to draw lots of stack heap diagrams. I know Nolan's seen quite a few of them before. And tables. I believe that came up the other day. There was something that kind of made sense talking about it as a table. But we will very soon see something that is explicitly a table. So we want to be very, very careful with our words. Kind of like list. The reason we say array instead of list, because list means something to most humans. Even though in Python, we only have list. We're programming, so when we talk to other programmers, when we're using Python and we say array, they know we're talking about a list. They know it's dynamic. We can add things and take things away. But arrays are much, much faster because it's an equation. So anytime the computer already knows where everything is array. We're going to talk about a lot of that soon. I have one on the list here that I just added it to the list. To do this. I only put it in the notes here to come grab the red marker and put that symbol y'all should be familiar with on top of it. Just because we can't access it does not mean we should access it. This is what the interpreter uses. The developers of Python did a really good job with it. Don't go messing with it. If you go messing with it, you have to go messing with your interpreter. And then you'll go down a big rabbit hole. There could be times that you need to use it. That's why we have access to it. But when you change this, you have to go reprogram your Python interpreter, which basically means you're making a child of the Python programming language. So you're no longer in Python, you're making your own language.
What does it say that we don't need to use? Is it new?
New.
Okay.
__ new __, and then define what that method does. We can override it, but when you do that, you're basically that means you need to get in there and create your own version of Python, which at least in this class, you're nowhere near ready for that, right? I see big head nods here. Some people might be like, oh, I want to get into that, and it can be interesting, but make sure you do that in like an isolated virtual machine so you can delete it afterwards. Something down the road you might see, because we can definitely add a lot of powers. Then when we make ours, we always have to do this method in it. So, and this is what I talked about this the other day, args and quargs. Talked about those the other day. When you develop Python, it was 1980s, so we abbreviated everything. Don't necessarily have to anymore, but arguments and keyword arguments, but what's really important there is the asterisk before. If you had C++, you worked with pointers. When we write our code, that means we have to use dash greater than symbol to create an arrow instead of the dot. Because we are more directly working in the RAM chip. We're pointing at a particular spot on RAM. But that was used in the creation of it. We don't necessarily create a lot of pointers in Python, so we don't spend a lot of time talking about it here. But we do use these pointers often. They always need to be our last parameter. Let me move self back a little. So dot, dot, dot. So all of our other parameters, and then those need to be last. And then inside of the method, something we often want to do is we can say super. So with the parent, like parent-child relationship, using that terminology, because a child has higher access to their parents' stuff than other people do, right? You have access to your parents' house. Your children have access to your house. Your neighbor does not have access to your house. So as an insider, there's more restriction, there's more levels of access. So a child can directly call its parent init method. Usually we have to go through a bunch of steps. Y'all might have seen that. Double underscore. We treat it like private. It's not private. This is going to be talked about in the next time. It's not really private like we have in other languages, but it's become convention that if you want to treat something like private in Python, you do put double underscores. Then any other programmer that sees it acts like it's a private variable, like it's inaccessible. But we do have access. But from inside, we do have the child has direct access to it. So the child can pass up any arguments and keyword arguments to the parent object. Set up default values, that's getting into typing and stuff.
What does that say in the parentheses you just wrote? It's just a little blurry on here.
Asterisk A and asterisk KW.
Okay.
Args and quargs. The words don't really matter. He wrote args and quargs, so most people tend to stick with that when he created Python. Von Rosen, when he created Python back in 1989, that's what he used. So most people stick with it. That way it's consistent. But what really matters is one asterisk or two asterisks. We can call it anything we want. If we have a better name, we can use that. Y'all have seen class notation before, right? So if we don't get all the way through this, because I wanted to end early and there's I have another picture here. That can wait till next week. That kind of wraps up our stuff here. Should we do a quick example? There's more to talk about next week, and then we can do the typing stuff. Actually, the more to talk about is going to be intermingled with typing. So why don't we do that next week? There's plenty of stuff to actively do, and we ran late the other night. It's been about an hour since break, so probably a good time to wrap up and then get into the, this is an active subject we learn by doing. I'm talking about this stuff, terminology you'll see on quizzes and things, tips, things that I picked up over the years, but it is an active subject. We learn to write Python code by writing Python code. I did that assignment yesterday, the ChatGPT stuff. So you have that to do because that will be an important thing for you to learn. Software developers, your chatbots aren't going away until civilization crumbles. So if you're heading into software development, you're going to make some chatbots. So you need to be familiar with those. It's good to look at some of the big fancy ones before you start making your own. You get a better appreciation of what goes into them and the work that's done and stuff too, with the result. So that's a lot of the talking about the objects. The rest of the talking about the objects intermingles into the lecture. Like I'll stop the screen share and draw a picture on the board, sort of thing. So that can wait till next week. There is a assignment that involves classes since the lecture is getting pushed back till next Monday, that can wait till after that. So I'll look through there and see if I can change the date on it. But the homework assignment that involves classes, if you haven't already done that yet, that can wait till after we talk about it in class. We still got plenty of time in the semester to do that. And there's lots of other stuff to do. Please use the time productively. Right? There's plenty of stuff to practice with what we've seen in Python, and you all have seen it before. So you can probably knock that out pretty quick. But there's more to talk about objects, so I won't necessarily require that homework until we finish talking about that. And then talk about some stuff with persistent data next week, as well as getting into more stuff with Django. That's what's on the plan. I don't think our book talks, most textbooks talk about sequential files, but has everybody heard of CSV files and JSON files and XML? That's how we want to store our data, because then our software is compatible with other software. And that will make clients happy, right? Customers happy. If our software works with other software that they have, they're going to be a lot happier than if the only way they can extend it is to buy other software that we make. The Apple thing, right? Apple does that a lot, but Apple has a very loyal following, so they can get away with it. We would not be able to get away with the only software this is going to work with is this other software we sell. Pretty much only Apple can do that. Microsoft can't even get away with that. So I want to look at those for persistent data. More stuff to talk about with object-oriented programming, but y'all have seen that before. We'll kind of look at inheritance. We'll talk about polymorphism some, but really polymorphism shows up a whole lot more in the mobile app development course, the next level, where we use the objects differently. Looking at inheritance mostly here and abstraction, which again with Python, well, we'll see that next week. We'll see fully abstract and concrete are two differences. Does anybody have any questions about the stuff tonight? I see head shaking no. Still going to count to 5. Okay, 5 seconds of silence. I assume that means nobody has any questions. If you have any, let me know. I've been checking, that's why I missed the message the other day to certain spots around the school. I keep getting no service. So if I'm standing in the wrong spot, my phone doesn't get service. But Ivy Learn messages and text messages should make noise on my phone. I'm going to be sitting in my office by the computer until 9:50. So Ivy Learn messages I will definitely be seen quicker. I guess just because for some reason at certain spots in the school, I have no service whatsoever. And I missed a text message the other day when I was sitting in my office waiting for questions at like 9:23 or something. Otherwise, if you have any questions, now till 9:50 is when I'm just going to be sitting here waiting for them. You can ask me questions anytime. Please use time productively. There's plenty of interesting things to do with Python, and check out ChatGPT. That's a tool you will use. It can be done with ChatGPT. There are some other chatbots that are better for writing code. You can try to have ChatGPT write some code for you, but there are chatbots that are trained specifically to you converse about the algorithm you want, and it writes the code for you and never makes a typo. Give that a try, because humans make typos and they get frustrating, right? We all see those at times. For those who haven't had me in class before, I always try to do at least one lecture that is not practiced and planned ahead of time. So you can see that even after decades, it's still like what you're familiar with when you write code. Typos happen, algorithms don't work out like we initially thought. And usually I plan and practice ahead of time so we don't waste a lot of class time. But we'll see that somewhere down the road. If nobody has any questions, that'll be it for this evening. I will see you all next Monday. Have a great weekend.
Have a great weekend. Bye.
Thanks, Chris. Have a great weekend.
You too.
Thank you.